Okay, welcome everybody. My name is Herman, and right now I'm going to tell you something about my thesis about graph pebbling. Graph pebbling is a technique that was invented to represent a proof about a theorem about numbers. And we're going to start with this theorem. It's called, so this is part one, it's called the Erdős Lemke conjecture. And it's named after Paul Erdős, who you might have heard of before, the traveling mathematician, one of his many ideas, and another mathematician called Paul Lemke. We're first going to look at an example with the number 6. So the divisors of 6, we first look at the divisors are 1, 2, 3, and 6. And now the theorem asks us to pick a list of 6 numbers that are all a divisor of 6. So all of those, we have to pick from these numbers, so we can pick multiple numbers of course, so we can pick 1.
Herman, sorry, dus ze zeggen in de chat dat ze je niet kunnen horen.
Okay.
Ik weet niet of dat te fixen is.
That maybe we can try. Can you
Ja, wat moet ik doen? Horen ze mij wel?
Weet ik niet. Een beetje vertragen.
Ja, dat klopt.
Iemand anders zegt dat ze je prima kunnen horen.
Oké, nou, dan gaan we gewoon verder. Want I tested it and it worked alright. It's not super clear, but hopefully good enough. So we pick 6 numbers. This can be any 6 numbers, but they all have to be divisors of 6. So we can also pick 2, 3, 1, another 1. And now, according to the theorem, no matter, or to the conjecture, well, it's proven, so it's a theorem, but no matter how we pick these 6 numbers, we can always make 6. We can always pick some of those 6 numbers that together sum to 6. So in this case, we could pick a 1, a 2, and a 3, and then we have 6. But we have other choices as well. We could also, we might as well, we could pick the 3 and then 3 1s, for example. So, like this. And okay. So we're going to do another example with 12. So now the divisors are 1, 2, 3, 4, 6, 12 also counts. So do we want to pick 12 numbers together? Okay, wait. I'm going to pick the numbers and you have to figure out a way to make 12 out of them. So pick some 1s. 2s, 4, 3, 2. Okay, so this is 12 numbers.
Yeah.
Does anybody want to make, can anybody tell me a way to make 12 out of this? Hands please. Ron.
Pick 1 4 and 4 2s.
Okay, so we have 6, 7, 6, 8, 10, 12. So that's correct. So hopefully you now get the idea. We're going to generalize this a bit.
Sorry.
We're going to welcome. We're going to generalize this to unknowns. So we're going to call those x, and they're going. They're going to have position in this list, which is just to reference that. So we have the first x, in this case, the second one, the third one, x3, x4, x5, and x6. And what I said before is they all have to be divisors of 6. So we add the requirement that the xi divides 6. For I is 1, 2, or any number of 6. And then, if we have that, then according according to the conjecture, there must exist a sublist that sums to 6. So we're going to do that using these positions. There exists a set S, which is a subset of all the possible positions in this list. 1, 2, 3, up to 6. Such that the sum of all those positions that we pick, all those xi's, is equal to 6. Does that make sense to everyone? Great. And then finally we can generalize it one step further. Of course, we can say, well, it doesn't just hold for 6 or for 12, but in fact for any number n, which is also has to be positive. If we pick n numbers, so up to xn, which are all divisors of n, then we can pick a sublist using the positions from all the positions up to n, such that those numbers sum to n. So hopefully you're now wondering how we can prove that this is actually true, because that is one of the big topics of my thesis, and we won't be able to discuss the whole proof today, but I'm going to give you an idea of how this works with graph pebbling, which is of course in the title.
So you're presenting a different proof than the usual one.
When this conjecture was first proposed, a few years after that, someone published a proof that is using induction on the prime factors. And then someone else, a couple of years later, came up with a different proof that uses this abstraction of graph pebbling, which kind of extracts the essence out of the problem. And that proof is, it's probably very similar, but it's, in a way, it's more clear. Yes. So I didn't come up with this proof, but it's a nice proof. Okay, so the second part, and by the way, feel free to raise your hand or interrupt me if you have a burning question. So the second part is about graph pebbling. So first, graphs. Well, you've probably heard of graphs, but I'm going to repeat it anyway. A graph is a collection of vertices, which I'm going to draw as circles. And between those vertices, there can be some edges that are connecting from one vertex to another vertex. And our edges also have a direction. And our edges also have a weight, which I'm going to draw in a box next to the edge. So this one will have weight 2. It's also and on these vertices, we're going to place imaginary pebbles. So every vertex, every circle can hold some number of pebbles. So for example, we'll start by putting 10 pebbles right there. And now we're going to play a kind of game. We are allowed to move pebbles around according to a rule. And the rule is like this. If you have two vertices that are connected by an edge that has weight k, and you have at least k pebbles on this vertex, they are allowed to subtract k pebbles here and add 1 pebble here. So in exchange for removing k pebbles from this vertex, you can put 1 pebble on this vertex. It's a kind of tax, a kind of transportation cost that you have to pay for this move. So we can do this here as well. We can say, well, let's make it 5. We remove 5 pebbles, and then we add 1 pebble to this vertex. And we could also move here, but we're going to do the same move again, so we have two pebbles on this vertex. And now we have enough to go over this edge. So we'll do so, 0 pebbles left, and we have 1 pebble here. So through successive steps, we have managed to get 1 pebble here from the starting configuration of 10 pebbles on this vertex. And that is kind of what graph pebbling is about. How many pebbles do you need in the worst case to reach some specified vertex? We're going to call this vertex the target vertex, which is represented by this bullseye. This is the target vertex. And this whole thing is also has a name. This is the graph G. And so if I would have had 9 pebbles and I would have put them all here, then no matter what I try, I can never reach this vertex with a pebble. So we say that we use a pi for this, that the pebbling number in this graph of this vertex T is equal to 10. Because it's the smallest number, such that no matter how you distribute that amount of pebbles over this graph, it will always be possible to get 1 pebble here. And that also includes cases where a pebble is already placed on this vertex. But in the worst case, you would put it as far away as possible, and then with 10 pebbles we can still do it. Okay? So of course this generalizes to any graph. So we're going to look at another example. Are there any questions so far? Amazing. So I've tried to make this explanation as accessible as possible because I know there's also some people watching who may not have heard of graphs ever before in their lives. So we're going to look at the pentagon now. So the graph G is going to have 5 vertices. That are all connected with bidirectional edges, so you can move in both directions. And all of those movements are going to have cost 2. And so, of course, you can already see, maybe you can see it coming. The question is now, if we pick any of those vertices as a target vertex, what will be its pebbling number? So, I'm going to say, for example, this will be the target. This will be the target. So now, what is, in this graph, the pebbling number of T? Does anybody have an idea? So, for example, if we would try 4, then we could put 2 pebbles here and 2 pebbles here. Then we couldn't really get there because we could try to put 1 here, and we could move this one in that direction as well. But that will not get us to T. And then so it's definitely more than 4. So using a counter example like that, we can say, well, it's definitely more than 4. And 5 pebbles, well, we could try to put it as far away as possible, like this, maybe. But this is solvable. Does anybody see how we can get a pebble here? Vessel?
Move a pebble to the right, from the 2 to the 3.
Yeah.
And then we have a 4 over there, and then we can solve it.
That's correct. So now, because this goes with powers of 2, you need 2 here, 4 here, and so on. So that also easily gives you an idea for the pebbling number of the path with these weights. So this is solvable. Well, we could try something else, maybe spread it out. Sometimes when you spread it out, it's actually becomes unsolvable. But then, well, we have 3 pebbles left, and we can just go this way. So indeed, the pebbling number of this cycle, which I also call C5 with a small 2 to indicate that every edge is weight 2, has a pebbling number of 5. for any target vertex T's. That's symmetrical, of course. Are there any questions so far?
Wait, why doesn't 4 work? Because if I put 4 there at the right bottom, then I can get one. to the
Right, so there are some solvable configurations with 4, but not all of them. Because if I put 2 here and 2 here, that's a possible way to distribute 4, but this one is not solvable. So the Pebbling number is a number, the least number such that it's always possible. You cannot find a counterexample.
Okay, but the 1 plus 1 makes sense.
Okay. So now we're going to connect this idea of graph pebbling to this problem with sums of divisors. And we're going to do that using a special graph. Every number gets its own special graph where we're going to somehow do something with those numbers. And that is the divisor lattice. So that's part 3 with the lattice. So again, we start with an example, and 12 is a nice example. And what is the divisor lattice, which we write with D? The divisor lattice of 12. What does it look like? Well, the vertices will be the divisors of 12. So we have 12, we have 6, and 3, 1, 2, and 4. This arrangement is no coincidence. And then these are all the vertices. And the edges will be the way these divisors are related by multiplication. So if I multiply 4 by 3, I get to 12. And similarly, 2 multiplied by 3 is 6. This is all multiplied by 3, and this direction is, of course, multiplied by 2. And those multiplication factors are going to be the weights of those edges. So like I did before with the box, every edge has a weight, and in this divisor lattice, the weight of the edges is going to be the multiplication factor. I hope this is not too small.
But you left out some edges.
Yes, so for simplicity, I've left out some edges, but in principle, we can add every edge that is a multiplication factor. So we could also go like times 6. We could also go this way, times 6. But we're going to forget about those edges because the figure is going to become very complicated. It is like the transitive closure, so you could regard it as the Hasse diagram. So that's a very technical term. Because, well, times 3 and then times 2, that is kind of the same as times 6. So I'm going to keep it to this diagram for now. Alright. I'm going to return, any question? No? I'm going to return to the example of 6 again. I forgot to do an example with right there. So we have those axes, 6 of them, and we're going to pick some list of axes. And I forgot to say one thing. Of course, we just talked about graph pebbling and pebbling numbers. And so the key question in this divisor lattice is what is the pebbling number of the top divisor, is number 6? Or previously when we had 12, what is the pebbling number of the number 12? And it turns out that, and this is the big gap that we're going to skip over, that is taking up many pages of my thesis. It turns out that the divisor, the pebbling number in the divisor lattice of n, of the number n, so the biggest number in the whole thing, is equal to n. And so in the case of 12, it will be equal to 12, and in the case of 6, so 6, it will be equal to 6. And that means that any distribution of 6 pebbles we can solve. Well, maybe you can already see it coming a little bit. We have 6 divisors here, and those are going to be our pebbles in a way, but not immediately because there are going to be some lists. So the key idea now is that when we place pebbles on this graph, each pebble is going to be associated with a list of numbers from this list. Each pebble is going to have its own sublist, essentially, and the sum of the sublist must be the same value of as the vertex it is standing on. And we start by making sublists with just one element. So, for example, x1 has the value 2. So the sublist containing just x1 can be placed as a pebble right here. And with one pebble. Yeah, and then also we can do x2. Then we can, at 1 we have 3 pebbles. x3, x4, and x6. And finally, so here we have 3 pebbles. Finally, we have 1 pebble here, which is associated with the num with x5. Does this make sense?
There are really lists of singleton lists.
These are singleton lists.
But you have lists of singleton lists.
So at every vertex, there are multiple of those lists, essentially. So yeah, you could say that, but that's very...
In this case, even the list could have had multiple elements.
This list will have multiple elements, yes. So these are 3 pebbles. Each square bracket list represents 1 pebble. And we start out with those lists containing just 1 element, which is each of those divisors. And in a moment, we are going to merge them together. So let's for a moment forget about these lists and just look at this configuration. This configuration contains 6 pebbles. And because the pebbling number of this divisor lattice is 6, we should be able, for this vertex, we should be able to solve it. So, Wessel, do you see a solution?
Yeah.
Can you tell me what to do?
We take the 3 and go to the left. So we are left with a 1 over there and a 3 in the left. And then we go up. And then we're done.
Exactly right. So, so that's the way to solve this. So we're going to go back in time, back to the starting position. So now what we're going to do is when we remove the pebbles from a vertex, we're also going to remove these lists, obviously, but we're going to, the lists that we remove, we're going to merge them together, and then together they will form a list that can be placed on the next vertex. Because these lists, they were all had value 1 when they were summed. So if you remove 2 lists and we add them together, then they will have value 2. And of course that generalizes to any number and any position in any divisor lattice. So when we go to 1, we say, well, these ones we'll get rid of. You will have a new one here. But because we have 3 pebbles, we also need to have 3 lists, and we can make it out of these lists. So of course, in any situation, those lists all need to be disjoint, because we cannot have the same x in multiple pebbles, and hopefully you can see that this works out. So now we have this situation, and now again we're going to remove 3, and place one here. So we're going to remove all these 3 lists, resulting in the big final list that has a value 6. So that is this one, this one, this one, and this one, which is indeed correct. Are there questions about this? Okay.
So you're talking about lists, but really they are sort of multi-sets, right?
Right, so I'm calling this list to make it a little bit simpler, but in the in my thesis, in the formal description, I'm using sets of positions, just like here. So I'm saying each pebble is associated to some set of positions in the list, some set of indices, and when you add all of those indices of the whole configuration together, they are a permutation of a part of all the indices. So you can never put the same index in two places.
So they're not multi-sets, right? They're sets.
Yeah,
Yes.
but you could say that so some of these x's might be the same, and then saying that they might have the same value. And
Yes,
saying
so
that so the x3 is the same as x4, doesn't matter.
Yeah.
Really. So you might say that they're sort of, no, that doesn't matter.
yeah, if you evaluate these x's to their value, so
It's the same thing.
I get your question. So I formalized this in the proof assistant coq, this whole proof. And then I had to think about a way to represent that simply. So there I am using lists, and there, this is just a list of natural numbers, and these are also just lists of natural numbers. And then the concatenation of all of those lists needs to be a subset of that, a multi-subset of that, or a permutation of that. But I'm afraid that doesn't make too much sense for most people. Okay. So I think I have time to look at another example, which is on the cover, which is in the cover of my thesis, this graph. And it is the divisor lattice of 60. So here we have 60. And I fit that. This. Okay, so if this is going too fast, that's all right. But we have 60 there. Then we have here we have 30. There we have 15. So this is the direction that multiplies by 2. Then the up direction is multiplied by 5. Or by 3, I don't remember. So here we have 1, obviously. Then here we have 5. I believe this multiplies by 5. And this multiplies by 3. So here we have 3. And here we have 6. So this multiplies by 5. This direction is 3. So now we have one distribution of pebbles. We have 6 5s. So 6 here. We have 20, so we need to pick 60 divisors. So that's quite a lot. I'm not going to write them out, of course, but I can say how many I have of each. So I have 10 3s and 15 2s. Well, and now the idea is that instead of telling you how this can be solved using a lot of single steps, I can also express it by saying how many pebbles will go over each edge in total. So it is in this direction, there will 5 pebbles will go into this direction. 5 pebbles will go into this direction. 2 pebbles will go into this direction. And 1 pebble will go to this direction. And to verify that this works out, well, 1 pebble moves here, so that looks alright, but maybe this doesn't work out at all. So, but we can verify that by looking at each of the vertices. So here we have times 3, so 5 pebbles times 3, that costs us 15 pebbles, but we have 15 pebbles here, so that works out. And then this direction was times 2, 5 pebbles times 2 is 10, so that also works out for the outgoing flow. Then on this edge on this vertex there is nothing, but we receive 10 pebbles, and we send away 2 pebbles at a cost of 5, because this edge is weight 5. So we receive 10 pebbles and we send away 10 pebbles, so that's also alright. And then here we receive 2 pebbles and we send away 1 pebble at a cost of 2, so that's also alright. So this pebble flow shows that gives a direct representation of how we can solve a specific configuration. Are there any questions about this? Okay. Then I'm going to talk, lastly I'm going to talk about some of the open problems of graph pebbling. And so graph pebbling for this proof was invented in 1989. And then immediately it was also considered interesting in itself, just on other kinds of graph. You could look at cycles or any graph you find interesting and see if you can find the pebbling number. And immediately some questions arose that have still not been solved. Some conjectures also that seem quite likely, but it's not clear how they could be solved. So, and a lot of these questions revolve around a way to multiply graphs, called the Cartesian graph product. So we take one graph here. I'm going to condense the vertices to point and not worry about the direction and the weight of the edges for now. Then we multiply it with this box symbol with another graph. And we get, well, the idea is that this example, you will see from this example how it works. You get this. And this graph contains both of these graphs in a certain way. So, and the edges, we can also label the edges as pairs of, you could say, coordinates in both of these graphs. So this will be A, x. This will be the A side, and this will be the B side of the graph. So this is kind of there, and then so this one, for example, will be B, but it will be also have Y, because this is the Y step. Z step, this will be A, Z. Well, this is this is a way to decompose grids into paths. But we can also take another graph. It's a bit more interesting. This triangle. We can multiply it with this path of 3 steps, and then we'll get this well-known chocolate bar. And we can also, if you multiply 2 cycles together, maybe you can see that we get a kind of torus, because all the cycles, every point in the cycle becomes a cycle in itself that is connected around. But you can think about it later. Okay, so does this multiplication of graphs make sense? Are there questions about this? Putting the sponge in a new place every time. Right, so now the question is, well, suppose we have, this is graph G1, and this is graph G2. Suppose that the Pebbling number in G1 of A is some known value K, and the Pebbling number in G2 of X is also known, say L. What can we say about the Pebbling number of the pair of those vertices, so A and X, this one, in the multiplication of those 2 graphs? So G1
Guess it's multiplied, considering it's a multiplication.
Right, we have a lot of examples to suspect that. So, for example, if we look at the example where this is all way 2, which is how it was initially studied also, then this would be 2, and this would be 4. And it turns out that the Pebbling number of this point is 8, and we can prove that using the proof actually that was also used for the Pebbling number of the divisor lattice. So, well, the question is then, is it the multiplication of those 2 numbers? We have a counterexample to this, which is, I'm just going to briefly mention it, which is when we have this 3-part multiplied by the triangle, then the resulting Pebbling number of one of the take 2 corners is a little bit lower. You can read more about that in my thesis. So then the question is, well, maybe it is at least bounded by the multiplication. It cannot be even higher than the multiplication of those 2 Pebbling numbers. And that question, or that conjecture, is known as Graham's conjecture. After Ronald Graham, who is also quite well known. And this turns out to be really difficult, apparently, because nobody has come close to solving this, I would say. In fact, we can look at just an instance of this question, which has also not yet been solved, which was already, when this was first raised, it was immediately asked, what happens to products of pentagons? We just saw one pentagon a while ago, and we concluded that the Pebbling number was 5. So what happens with products of pentagons? So, draw this again. this, bidirectional, way 2, and we said, well, if we take one target vertex, then the pebbling number, so I call this C5 with unit 2. Then the pebbling number of the target vertex is 5. So maybe then, if we take 2 of those, and we take some arbitrary target vertex in there, because of course they're all the same, then maybe this is 25. And it cannot be lower than 25 because this graph has 25 vertices, and if it would be, we can always place one pebble at every vertex except one single target vertex, and then we cannot move anything because at no vertex there are enough pebbles to do a move. So the pebbling number is surely larger than 24. And if Graham's conjecture would be true, then it would be less than the multiplication of this pebbling number with itself. So then it would be less than 25. And so in conclusion it should be 25. So this would immediately solve this question. Well, this question was actually solved, and it was confirmed that the pebbling number of this product is 25, using a rather long and complicated proof with a lot of different case distinctions and configurations. But then we can just easily scale the problem up, and we can say, well, let's just multiply it again with a cycle and pick one of the vertices of this graph. Is this 125? And this is still not yet solved. So if you're looking for a fun problem to work on, you could try to figure this out, or some of the other unfound pebbling numbers. And you might think, well, can't we do something with a computer? But there's no method for that yet, because the number of possible configurations explodes. And so, especially this problem, which looks so temptingly simple, like now maybe it makes so much sense that this pebbling number should not exceed, well, it seems to make sense, should not exceed the multiplication of those numbers. But because this is already so difficult, then surely this must be even much more difficult. Okay, that's the end of my presentation. Thank you for your attention. Are there any further questions?
Were you able to prove some things that weren't proven before?
I can tell you something about that, maybe. So I did, in my thesis, I mainly did two things. The proof of the Erdős-Lengte conjecture via graph pebbling, I formalized it in Kok, and I also changed it a little bit, because the original proof was described in just a few pages with a lot of gaps. It was kind of sketching the direction of the proof, and I couldn't completely work it out, because it seemed, the induction hypothesis didn't seem to fit. I still don't know how it should exactly work. But I changed it a little bit, resulting in a lot of pages of linear inequalities and case distinctions. And that works out, and I also formalized it in Kok, so every single small step of that is confirmed to work. And the other thing I did is answer the question, is it ever necessary to move pebbles back and forth over an edge? So I have some sort of graph, doesn't matter, it can be huge, and it can have all kinds of different weights, and I have some target somewhere. Is there somewhere in the world a configuration where I would first need to move pebbles over some edge in one direction, then, I don't know, do some things, and then move pebble back over the same edge. So that would be an edge where you can go in two directions. And well, it doesn't seem very productive to do so, because then you just waste on tax, on transportation cost over this edge. But that's not a proof. And so I did figure out a proof that is using the idea that I showed with the big divisor lattice, the flow values. So what I do is, I think I have time to explain it, but let's first, are there first other questions to the rest? Okay. So it says, if you have a sequential solution, then surely you can translate that into a flow network, into flow values. So the flow values would be, if I have this thing again, and we had, let's think, 3, and we had a way of 2, way of 3, this was the target. So then instead of having a list of steps, we could record how many pebbles are moved, and then we see, well, one pebble is moved in this direction and one pebble is moved in this direction. So we can transform a sequential solution into this kind of flow network. And then this flow network satisfies this condition that at every node, at every vertex, the number of pebbles coming in plus the number of pebbles that are already there are at least as big as the number of pebbles going out, because I cannot move away more pebbles than I send there. And so I call that feasible. So this results in a feasible flow network. When you have a sequential solution, there's also a feasible flow network. If there would be bidirectional flow, so if I would also have an edge in this direction and there would also go a pebble in that direction, then I would get something like this. So I hope it doesn't get too confusing. So this is maybe not feasible anymore. 4 here or something. So that's the situation that we are wondering if it is necessary, where we go back and forth. So if that situation would be necessary, then we would get a flow network like this. But then we can say, well, we can cancel these against each other. So these both become 0. And then it's still feasible. Because obviously the number of pebbles that we get in total decreases by 1, but the number of pebbles that we need to send away also decreases by probably even more, because this edge might have a big weight. So it's still feasible. So then what I proved is that every feasible flow network can be solved using steps. So when you have a feasible flow network, you can find a sequential solution that it corresponds to. And it means that there's also a sequential solution that corresponds to these flows cancelled out. And so it is never necessary to go back and forth, because when you would go back and forth, you can get rid of going back and forth via the flow values and then cancelling them with each other. Does that answer the question?
Yes, it does.
Great. Yes.
I have one more question. Because in all the examples with these divisor lattices and actually of the theorem of Erdős and Lemke, you seem to have a lot of leftover space because there were multiple solutions and things didn't seem to be unique and things like that. Is that always the case, or are there, I mean, is this best possible in a sense? You think about that?
Yes, because all of these numbers could be a 1, because any number that we pick, 1 will be a divisor. All of these n numbers could be 1, and then the only way to get n back is to take all of the 1s together. And then you have n. Yes, so it's the best possible value.
And this was also a very special case of a more general theorem,
Yes.
right?
So
Which of course is very complicated and confusing, so it's good that you treat this one, but maybe you should mention at least the general
yes,
statement.
it's true. I was planning on saying something quick about that, saying this is a special case, but I forgot to say that, I think. So in general, there are two numbers, n and d, and I have to look quickly how it works. then we have not n integers, but we have d integers.
And D is a divisor of n.
And these are all divisors of d. But yes, so these are both actually 0, and d is divisor of n. So we could say, well, here we have 0, here we have n, and then somewhere there's the number d. Then we have all these numbers that are divisors of d. No, that's not correct. That are divisors of n. So maybe there can also be one here. This could be one of the x's. And then there is a sublist that sums to a multiple of d. So it's 0 modulo d. And it's smaller than n. So we could have some. So maybe d is a very small divisor of n. So maybe d is somewhere here. Then we could have all sorts of x's here that are all divisors of n, because the x's need to be divisors of n, not of d. And then there is some sublist that is smaller than n, but that is also a multiple of d. So maybe there's a sublist that sums to 5d. And that's what the full conjecture says. And then the proof for this conjecture is actually even more general. That's using something with greatest common divisors. But you can look that up in your free time.
And the graph pebbling proof also works for this conjecture, or?
Yes, yes, and a more general one. So one question that remains is, does the graph pebbling proof correspond exactly to the first proof, the other proof for this conjecture? I didn't study that because the first proof is 20 pages long with a lot of fluid language and a lot of side cases, and I didn't really have the energy for that, but it would be an interesting question whether they are exactly the same or they're in some sense different. Okay, I think this is a good point up.
I had one serious question, but let me ask the two non-serious questions.
Yes,
The first non-serious question is at the back of your thesis. I saw a picture. Who is that?
that's me.
Uh-huh.
With a chessboard with little glass cups with pebbles. So I've visualized the pebbling game that way.
Okay, the second non-serious question is on your shirt I see a graph, and on the back I also see a graph.
That's
Do they have
very
anything to
fun.
do with this problem, or are they just arbitrary?
Oh, now this is actually a very great question because I have just time to explain this. So the proof of the Ayers-Levitt conjecture via graph pebbling goes through something called a hypercube. So we have this divisor lattice, and as you might realize, a divisor lattice is like a multi-dimensional grid that can have, well, it can have some steps of multiplications by 2, multiplications by 3, and by 5. But it turns out that any of those multi-dimensional grids, we can make it out of a hypercube. And this is actually the illustration of that for a simple case. So this is a 4-dimensional cube, and I'm not sure if I can draw it on the board, but I think I can try it. Because it's actually a very beautiful picture. I found it on Wikipedia, and then I thought, this is so nice, I need to get it in there somewhere. You just make 8 points in a circle. Then you make another 8 points that are spaced out a little bit further. And then we have to connect some of those points. And here you can already see the first cube emerging. another cube, hiding in plain sight. And then of course you have to connect them. And someone said to me, well, that's a really nice picture, I will print it on a t-shirt. So that's this t-shirt. And now we can fold this hypercube into this grid. The mathematical term is a retraction. We can retract this to this. Well, that's not immediately clear, but it becomes very clear when you draw the right lines. So we have this face right here. And we have this face right here. And we can glue them together. So we have kind of two cubes. We're taking the opposite faces of those cubes and we're gluing them together. And these edges, they will kind of come to each other. They will become the same edge. And when we're pebbling on the hypercube, with the graph pebbling, what we do is we translate a pebbling solution on the hypercube to a pebbling solution on maybe this grid. And we can say, well, if pebbles are moved over this edge or over this edge, it doesn't matter anymore if we make them the same edge. We can just also merge those pebbling steps. So if we merge these two together, which is what is happening here, then we get this shape. Okay, it's not very.
Herman can't cheat for this one because it's on the back of his shirt.
Yes. Right. That's a good point. So this is actually the divisor lattice of 60 that we see here. So we could stop here. But if we have another number, so maybe this is 2 and 2 and 5 and 5, so we have 100. Maybe this is the divisor lattice of 100. Then we can go another step. We can take this line here and this line here, and we kind of, like we have a milk package, we can kind of squeeze them together. So this line goes to this line, and then we can get this shape. And so that's symbolized in this t-shirt. Well, I think that's a great point to stop.
Henk still has a question, I
Oh.
think, and there's 2 minutes left, so.
Okay, thank you. I have a question that relates to Wiener's first question. So in this divisor lattice, it seems like if you push the pebbles on one, that's the largest distance you have to use to go to the target. So if you're not allowed to put any pebbles there, can you then improve the result? And I think it has also an interpretation in terms of the Edwards-Lemke conjecture, because you say you only allow n which is not prime, and you only allow proper divisors, which is sort of the natural. So it is about the earlier version you have with only the n. So if you exclude one as a possible divisor,
Yes.
and you only allow non-prime n,
Okay.
can you then improve the size of the set that you need? Or can you still find an example where you need n divisors?
So I think that would be the case, because in this case you were saying we should remove this, essentially. So if we are not allowing ones, then maybe the worst case becomes some 2s and 3s together, so we will get to the desired sum much quicker, it seems. So then we could try to find the pebbling number of this 100 in this graph. Well, I don't know the answer. That would be an interesting problem to say, but I suspect it will be less, yes, because, well, you're already closer to the target. And a prime number that would just have very simple multiple divisor that is.
Yeah, so if you exclude one, you can only put pebbles on the number itself,
Yeah.
which is a good feel.
Okay. Does that answer the question? I don't know the answer.
Okay, that's all.
But it's an interesting question, I think. No more questions. And it's also 12:01, so then we can stop. Thank you again.